have endured Jasek's, what, 2 or 3 sessions of this mind-boggling SMD, surface-mounted devices. We're going to actually see it work so that you actually know what he put together is going to function. It's a little difficult when you watch him work with the little vacuums to pick up these pieces, or the little tweezers and pick them up and try to solder them in place. Very exciting. One thing I did learn though, and I learned it very well, I'm not going to make anything with a surface-mounted device.
Another session about SMD devices, fourth in a row. This time I'm going to show you how the device that I built during the previous presentation actually works. I got it to work and I will show you. But first, let me tell you what actually went wrong. So after I removed the board and installed it second time on the preheater, I actually didn't install it correctly, and one of the mounting posts moved the components. That's why they were displaced. So these were 3 current limiting resistors, 1 capacitor. Not very big problem. I did the entire rework, soldering leads, everything. It took me about 15 minutes. So you see that it was not very big, and actually I filmed the entire process. Where's the mouse? So this is slightly sped up. So right now I'm removing the components. You can see they are crooked. Now I'm cleaning the old solder. Again, applying new solder. Placing components. And now time for rework. So you will see how this component nicely snapped into place. It's done. They're soldered. So, as I told you several times, it has to be cleaned. And this board really needed cleaning. I actually spilled a lot of flux. There was a lot of resin on the board. I had to clean it. I just use, this is plastic cup from yogurts with cereals. So nothing special. Isopropyl alcohol. Properly, you should use anti-static brush. I'm just using toothbrush. That's it. So I went to rinse it underwater to wash off the dirty alcohol. Now I rinsed it again with clean alcohol to absorb the water. And it's pretty much done. Now I'm soldering the leads. That's it. So as I told you, this is sped up a little bit, but everything took 15 minutes without rushing too much. You can see it's very simple.
Except of course the video looks rushed.
Well,
yeah, you're moving real fast.
See what practice does. Okay, so one thing that I wanted to show during the previous presentation, I started to do it, but I didn't have time to show what are the consequences, is applying too much solder to the parts. I mentioned about it during the second part, during the second presentation, during the general meeting, that you should be very careful how much solder you put. And this is one of the problems that I have with this method, that it's very difficult to control how much solder you apply. So I did this on, this is inductor, this is the output path, this actually inductor couples to the output and provides power to the amplifier, this is the amplifier. And you can actually, these are inductors. It's impossible to see without magnification, almost impossible. You can see that it is slightly crooked. Now you see how bad it is. It's pretty much horizontal. So you have to be very careful how much solder you apply to the parts. Too little is bad because then you will not have contact. Too much is also bad because you will have something like this. So what am I gonna do? First of all, I want to show you that it actually works. Second, I want to show you how to do some simple measurements. And these measurements can be done with tools which are accessible to pretty much everybody. Maybe they are not the cheapest, but they are definitely affordable. It's possible to do much more measurements, but today I will just show one. So what is actually this device on the board? It's an MMIC monolithic microwave integrated circuit made by Skyworks, and this is broadband amplifier spec'd from 0.1 to 6 GHz. Turns out that it works very well, even pretty much from zero. Typical gain, small signal gain is 20 dB, intercept power, blah, blah, blah. One thing that I don't like about this amplifier is high noise figure, about 4 or 5 dB, but I'm going to use it as output amplifier for my SDR, so this doesn't matter that much. If you would like to use it as an input amplifier, well, then that's a different story. So how do you measure how the amplifier works? First of all, I want to see how it works on HF bands. So the simplest method, take a generator, connect the amplifier, take high frequency voltage voltmeter, and measure what is the output from the generator, measure what is the output from the amplifier, divided, you have amplification. What are the disadvantages of this method? You only measure at one frequency. If you want to measure at many frequencies, you have to go from one point to another, take the measurements, graph them. Another problem with just the simple measuring is that out-of-band noise may affect the result. So if you have very broad measuring frequency range, so you have broadband voltage meter, you will measure the noise over this entire band. And your signal actually, even if on the spectrum analyzer the noise level is much lower than the signal, if you integrate it over the entire band bandwidth, you may end up with something what is comparable with your signal. So solution, add a filter in front of the voltage meter. And this is schematic of how it looks: generator, your device, voltage meter. That's it. This is very simple. Well, as I said, you can take many measurements, but this is tedious, boring, prone to mistakes. If you only have these tools, when people had only these tools, they were usually taking only a few measurements, then fitting line to it. This is good approximation, but what will happen if you have some, for example, very sharp resonance that we miss? You will completely miss it. You will not know about it. So this process can be easily automated, and this is done in a device which is called frequency response analyzer. So how such device is built? We have such components: switch generator. This controls where is the frequency, oscillator which can be tuned, of course our device, bandpass filter because you want to get rid of the noise, out-of-band noise, signal amplitude detector, and graphing device. Simple as that. And this is schematic of such device. So this is our switch generator. It generates sawtooth voltage, increasing and dropping, and we have our voltage controlled oscillator. So how does it affect the generator? When the voltage rises, the frequency rises. So we go up in frequency, and then voltage drops, we go back to the start. So we have, if you look at the frequency coming out of this, we have also similar solve. Then we have our device filter, which filters out everything except our signal, and this filter must be matched with generator, because you want to cut everything from your input except your signal, which is coming from the generator. So this filter also has to be tuned. Then amplitude detector and graphing device. Usually it used to be oscilloscope. And this swing generator controls horizontal axis. The signal from the amplitude detector controls vertical axis. So the higher the signal, the higher the beam goes. And because this generator is connected to horizontal line, it goes from this, like this. So we go from low frequency, very little signal, then we get to our band pass, high signal, high level of signal from the detector, again, low level. This sounds very like spectrum analyzer, and it is. Why do I mention this? Because if you're going to take amateur extra exam, there are several questions about spectrum analyzer. So I want to tell you about this, so you will not have to go through this topic. What are the similarities? The measurement path is pretty much identical. You don't need the generator. If you buy spectrum analyzer, you can actually add switch generator. This is the voltage controlled generator, and this is not very expensive. For example, in Rigol you can add tracking generator for like a couple or $300. Compared to the cost of the spectrum analyzer, it's pretty much nothing. So this is how it looks. This grayish, barely visible, this is the part which we can remove from the frequency response analyzer and exotic spectrum analyzer. Okay, any questions about this?
So it can be an input to the device under test?
Anything.
Okay.
So this can be a generator. The difference between spectrum analyzer and frequency response analyzer is that you don't feed this device with anything. So this can be your radio, this can be a generator, this can be anything, whatever. You don't feed it anything.
Well,
You just take the output.
I guess the term response analyzer means it's responding to something you're generating.
Yes. In response analyzer,
As opposed to a frequency analyzer, which just measures whatever frequency is coming in
yes,
from outside.
here you provide the input to the device, and this device can be completely passive. It doesn't have to generate anything. Here you just look at the output, whatever the output is. If this is passive device, it will be noise. If this is active device, for example, you can look at your transmitter if you're not transmitting spurious signals. Then you connect to spectrum analyzer and you look how it looks, how it looks what you send to the antenna. If your transmitter is okay, it will look something like this. If you have spurious signals, you would have some spikes here. So that's the difference. More questions? It's showtime. So let me connect the device. This is the board with leads. And let me show you what I have here. This is small device. I got it on Kickstarter. This is called Red Pitaya. And this is actually software defined anything. It has FPGA here, which takes care of processing and generating signals. There are two are processors in this FPGA. There are two digital to analog converters which provide signals, two analog to digital converters which measure the input, actually sample the input, and you can connect it to the network. Here I have wireless interface. So first let me connect to the network. Come on. Network. Where is network? Okay, it's connected. Great. And by the way, you can use, I'm using a laptop, but you can also use a tablet with this device. You can connect anything what has Wi-Fi connectivity and web browser.
What is that? Is that a micro design, right? Driving the A to D or D to A? You said?
Yes. So you have FPGA which generates signal, sends to DAC. You have analog signal on the output, and you have ADC.
So you got an FPGA engine there generating the signal, you said, synthesizing the frequency?
Yes,
in?
yes.
Okay.
And these are the applications that I have. By the way, don't get too excited about it. I liked it at the beginning. Right now I consider it as an educational toy. For many reasons, but okay, it's worth the device, but for serious work, you should get something else.
Something that costs more than $10,000.
Not necessarily. Rigol should be fine, but something would cost less than more than $500.
Who is this Rigol? I just keep hearing this show up.
It's
it seems to be the new kid on the block or something.
Chinese
Is this the new Asus or something?
This is Chinese manufacturer.
That's a Chinese manufacturer?
Yes, but they are not
They
your
make instruments.
everyday Chinese manufacturer. They are all OEM for, I think, Agilent.
Agilent?
For one of the big players. So they're
Which got changed. It's now Keysight.
Keysight.
Again?
Yeah, they got split again. You know, these equity traders have to buy and sell companies every other week.
I don't remember which one.
Commission.
They are building devices for one of the big names. So
Well, I was at a tech school the other day and saw this Rigol instrument. I said, where do these guys come from? You know?
these devices are worth the money.
They are, okay.
They are.
Because I remember in Ritsu's blowing out on me, spectrum analyzers. And
Okay, so this is what we have. This is first I have to calibrate it. So what I did, I connected the input and output with a barrel, and you can see that this is way below 0 because I have attenuator here. If I connect the output from this analyzer directly to the input of the amplifier, it will be way overblown. So I have to attenuate it. So let's bring the signal to 0.
How much attenuation are you using?
30 dB. 30 dB. Okay. So it's calibrated nicely at 0. And let me connect.
And that's the output of the FPGA that
This is
generating
the-
some kind of.
This is the noise that the ADC picks up.
Oh.
And this is quantization noise, all kinds of noise. And actually the noise that the ADC picks up is pretty big. This is one of the my complaints about the device, that's the noise that it picks up is very good. Okay, power up, minus 20 dB. What the hell? Oops, I connected it in reverse. But I did it on purpose. So what I'm measuring here is what is called in datasheet reverse isolation. This is isolation that the amplifier gives you from the output to the input. If you apply the signal to the output, this is how much it will be attenuated at the input. And according to the datasheet, it's 23 dB typical. We have around 20-ish, a little bit below 20. So should be within spec. So take two. Let me reverse it.
You mean unreverse it?
Unreversed.
Reverse the reversal.
Reverse the reverse. Yes, then we start. So right now we have completely different situation. Don't look at this. This is end of the band, so it shows many different things here. But here you see very nicely 20 dB. Let's look at the data sheet. This is what we should get. Small signal gain measured at 2 gigahertz. Well, I'm not measuring at 2 gigahertz, but minimum is 19 dB, typical is 20. We have very nice 20 dB gain. So,
What's the high end frequency of that chart?
for the device, it's 6 gigahertz. For this board, this is FR4, so I don't expect it to go up to 6 gigahertz, but should be usable up to, I don't know, 500 megahertz, 1 gigahertz, I don't know. I have no way to measure it.
Now that signal you were putting through it, that's doing a frequency scan from what frequency to what? What's
From
the top?
0 to
What's the top frequency?
60 megahertz?
6 megahertz?
60.
60.
Yeah,
60. So that's 0 at the bottom, all the way to the top
Yeah,
is
so
60.
this is 0 here, 60 is here.
60. So
Easy.
it's pretty flat all the way across
Yeah.
in frequency.
Well, from device which is spec'd up to 6 gigahertz, I would expect to be flat.
Yeah.
And what kind of power is it?
20 dBm. And so you put 0 at the input, you should get 20 dBm at the output. So what else I could do with this device? Well, first of all, I don't have enough time. Second, I have the equipment that I have is insufficient for this measurements. But what else I could do? Noise figure.
You've got a noise source.
Yeah, you need a noise source.
You have a noise source, don't you?
Yeah, but you need controlled noise source. And actually, controlled noise source can be very expensive if you look at. I'm not talking about new. Look at eBay. The cheapest one, decent, I found was around $100. Semi-calibrated. If you look at brand names, you go into thousands. What else can we measure? Reflection coefficient, so how well it's matched, the output, the input, compression point. This is very important. This tells you how much power you can put at the input before you start to get distortions. But by the way, let me show you one more experiment. Let me show you why I need this attenuator. So I'm removing the attenuator, connect directly. this is what you get if you overdrive the amplifier.
Yeah.
Not pretty.
It's actually ugly.
Yeah.
So one last thing that I want to tell you, why should you care about this reverse isolation? Most of the time you don't, but there may be situations when you do, and I can imagine too.
Phasing circuits.
Yeah, but something what you can find in, but if you experiment with, yeah, this is one, and another scenarios that I came up with that you can encounter in your work as engineer is two. You have, for example, one situation. You have a sweeping generator, very stable amplitude, controlled, and you use resistive divider. One part of the signal you send to this amplifier, second part goes to somewhere else. But you need to have stable amplitude, you rely on this. And accidentally you forgot to terminate the output of this amplifier. What happens? All the power gets reflected. So you have 20 dB amplification on the way up, reflects 20 dB attenuation on the way back. You end up,
Oscillator.
well, you have oscillator, so you don't have to oscillate. But what happens? You have pretty much identical signal coming back with random phase. And this signal interferes with the signal from your generator.
Right.
And when you sweep, this phase difference changes. And you get amplitude sweep from 0 to whatever. And you have no idea what is happening. So you have to take into account.
So does that wind up being stochastic noise, or is it
No, it's
evenly?
just phase difference. Because when you go through the amplifier and back, you have delay. And this translates into phase difference when you change the frequency. Another situation is that you have very stable generator, one frequency, again, signal splitter, your amplifier, antenna matched, so you don't have any reflection, and you rely on the stability of the signal, on cleanness of the signal. And everything is matched, everything works perfectly, but you see that you get junk in the signal. What is going on? Well, you discovered that you pointed the antenna at window, and you happen to have a transmitter outside. So the signal from the antenna works both ways. It transmits and receives. So you transmit your signal, but you receive the signal from the transmitter outside. This signal gets to the amplifier, to your device, and adds to the signal from the generator, and you get junk. Okay, that's it.